Okay. So just to go over it again, if you have the derivative with respect to x of some exponential function b, whether it's between 0 and 1 or greater than 1, then its derivative is itself. Just like e was its own grandpa, any exponential function is going to be itself times the natural log of the base. And then, of course, if the exponent is more than just x, it's the chain rule. So why is it that the base e is its only, or the only one that is its own derivative? Well, if we use this rule, the derivative of e to the x is going to be itself e to the x times the natural log of the base. Well, the base is e. Guess what the natural log of e is equal to? It's equal to 1. Okay? So it turns out that e is the only exponential function that is its own derivative. Pretty special. That's kind of neat when you think about the natural base, right? Of all numbers to choose for the exponential to be its own derivative, the natural base, Euler's number, is the only one that is. All the others are constant multiples of themselves, vertical stretches or vertical dilations, one or the other. So, pretty cool. All right, example 4, an application real quickly. At what point on the graph of 2 to the tth power minus 3, so we have an independent variable t not x, does the tangent line have a slope of 2? I'll let you do it. At what point on the graph of this function does the tangent line have a slope of 2? While you're working it out computationally, I'm going to go ahead and sketch it so we can refer to it graphically. All right, so if you're looking at it graphically, remember the minus 3 will move the function down 3 units. There's usually a horizontal asymptote at y equals 0. So whenever you have that vertical shift, that's going to be the y-coordinate of your d value, or your asymptote, sorry, horizontal asymptote. So we have a horizontal asymptote at y equals negative 3. The y-intercept is negative 2. It's an increasing function. So I just kind of went over here to the right and randomly drew a slope of what I thought was 2. And we can visually see now exactly what we're trying to find. So our method is, okay, I need to find the derivative, and instead of plugging in a value of t, I'll set it equal to 2. So dy dt, instead of dy dx, is going to be, what's the derivative of 2 to the tth power? 2 to the t times natural log of 2. Good. And then minus 3 goes away to 0. So now instead of plugging in for t and evaluating it, we'll set it equal to the slope we want. Okay? And now we'll solve. So to solve, we want to isolate the 2 to the t, so I'll divide both sides by the natural log of 2. And now how do I solve for this? How do I get t out of the exponent? Well, you could take log base 2 of both sides. If you remember from pre-calc, that's the inverse of exponentiating base 2. But we typically don't use bases that aren't e in here. So what we'll do now is we'll take the natural log of both sides. Take the natural log of both sides. And we've already seen this today. Logs essentially linearize exponential functions. So you bring the t out front, equals the natural log of this, 2 over the natural log of 2. And now all we got to do to solve for t is divide by the natural log of 2. So we get this wonderful thing, the natural log of 2 over the natural log of 2, all over the natural log of 2. And that's it. That's the exact answer. That is the location where the derivative is 2. Now let's think about like a multiple choice, no calculator section. I probably wouldn't put that as an answer choice. What can we do in the numerator that you remember with properties of logs to get rid of the complex fraction look? Here's two more rules. We know that the natural log, or logs in general, of a product, AB, turns into the sum of the logs. And similarly, the natural log of a quotient turns into the difference of logs. So I can actually write the numerator as the natural log of 2 minus the natural log of the natural log of 2 all over the natural log of 2. Would these then divide out on the left? No, because it's a term in the top. Could I factor this natural log of 2 here out of that natural log? No, because that's not a factor. That's part of the function. That's the inside of the function. So the only thing you're going to be able to do, aside from listing it like that, is to split it up and put each term over the entire denominator. It's just another way to do that. And you might want to do that because the first term is 1. So 1 minus the natural log of 2 all over the natural log of 2. Do these natural log of 2's divide out? No, because then you're just left with 1 minus natural log, and that doesn't make sense. So simplified answer, I would say either that one or that one. Not a real pretty number. If you want to know what that is, you could type it into your calculator. I'm not real curious about it. Okay, evaluate the following. We have the derivative with respect to x of 7 to the negative 3 over x. How do we know that that's going to be exponential-ish? Yeah, there's an x in the numerator. Now, here's a good answer choice for a test. Negative 3 over x times 7 to the negative 3 over x minus 1 times whatever, the chain rule. What did I just try to do there? I tried to use not the product rule, but the power rule, right? Where you just multiply and subtract. Multiply and subtract. Does that work for exponential functions? No. Okay. So whenever you have a x in the exponent, it's going to be exponential. So let's go ahead and rewrite this. That's 7 to the negative 3x to the negative first. And now I can use the exponential rule. It's going to be itself, negative 7, or 7 to the negative 3 over x, times what goes next as part of the exponential rule. The natural log of 7. And then times the chain rule, which is going to be 3x to the negative second or 3 over x squared. That's the chain rule. So you can maybe simplify that in your head. Negative 1 times negative 3 is 3x to the negative second, which is 3 over x squared. So there's an answer choice for a test. Guess what most students who do these exponential things tend to forget to do? They kind of remember the chain rule. Yeah, they forget the natural log most of the time. That's what I see. So remember, only base e is the one that doesn't need the natural log of e there because it's 1. Okay. If you do this one, it's exponential. Well, look what's going to happen. The derivative of e to the blob is itself. That's e to the natural log of x times the natural log of e, which we don't need, times the chain rule. What's the derivative of the natural log of x? Well, we haven't learned that yet, have we? So what the heck is this doing in this section if we haven't learned the derivative of the natural log of x yet? Well, it means that there's another way to do it. So you should learn to simplify early and often. What does e to the natural log of x simplify to? Well, e to the natural log of x doesn't simplify to 1. E to the natural log of x simplifies to x, right? You're composing two inverse functions. So this is equivalent now to the derivative of x with respect to x, which is in fact 1. Okay? So that's again why it's important to rewrite the d dx, because I guarantee an answer choice would be x for people who forget to take the derivative, or, you know, if you call that second line there derivative of 1, then the derivative of that's going to be 0. So if you're just rewriting, make sure everything else outside of that stays intact. All right, this one here, This is going to be a chain rule. Everything looks ready to go. So I first notice that it's blob squared. And I'm not interested in expanding that. So I'll just multiply with the chain rule. So it's 2 blob to the first. And then times the derivative of the blob. Well, that's 2 terms. What's the derivative of e to the negative teeth power? Very good. It's itself, e to the negative t. Don't need to worry about the natural log of e. Times the chain rule, a negative 1. And a lot of students forget that negative 1. For some reason, when it's just a negative x or a negative t, they forget the chain rule, forget to multiply by negative 1. And then plus, what's the derivative of e to the t? My own grandpa. Yep, there it is. And we're essentially done with the derivative. Looks good. Now, if I rewrite these, I can write that as e to the teeth power plus e to the negative teeth times e to the teeth power minus e to the negative teeth. What do we call those 2 factors compared to each other? Conjugates. Yeah. And when you multiply 2 conjugates, you always get a what? Difference of squares. So maybe we could expand those out. What's e to the t times e to the t? E to the 2t, right? When the bases are the same, you add the exponents. The inside and outside are going to cancel. What is e to the negative t times e to the positive t? E to the 0, also known as 1. So you're going to get a 1 on the inside, and you're going to get a minus 1 on the outside. Those cancel. And then you're left with negative times positive is negative. E to the negative t times e to the negative t is e to the negative 2t. Yeah. So there you go. That's kind of a nice way to put it back into a final condensed format. Okay, go ahead and try this one on your own. This one might take a little bit of rewriting, and it's not going to be very fun. Ooh, gross. I'm kind of getting excited about it. All right, let's see how you're doing. My first step here would be to rewrite it. The number one thing that students forget to use in the chain rule is when you have functions written in condensed form, sine squared, cosine cubed, whatever. So it is probably worth a rewrite to write it in the expanded form like I have below. So it's first of all a product rule, yeah? So the derivative of x squared is 2x times the second one goes along for the ride, which you can write that now back as sine squared of 4x. So there's one of the terms. For me, it's the first one. And then plus, now I just rewrite x squared, and I move on to the next part. So this is going to have how many layers in it? The next factor. 4 layers. Yeah. The outermost layer is 5 to the blob, then blob squared, then sine of blob, and then the blobbiest of blobs 4x. So you're going to have 5 factors here. I'll color code them. Let's start with brown. The derivative of 5 to the blob is itself 5 to the sine squared of 4x times what? Natural log of 5. So make sure you finish that rule before you go on to the next. Don't forget the natural log of 5. Times the next layer is blob squared, which is 2 blob to the first, and that blob is just sine of 4x, times the derivative of the next layer is sine of blob, which becomes cosine of the blob, and then finally the derivative of the innermost blob, derivative of 4x, is 4. Yeah. So there it is. And then, of course, if you wanted, you could factor out a 5 to the blob. That's what's kind of typical when you have these exponential derivatives with more than one, when you have the product rule, you're going to be able to factor it out from both terms because it's going to be there. It's in part its own derivative. So that looks kind of gross. I'm just going to let that simmer for the rest of the year and never come check on it again. Okay, we'll even turn the stove off on that one. Okay, do this one very quickly if you haven't already. We'll finish up with this woolly booger. Is this going to require the product rule? No. Is it even going to require an exponential rule? Nope, it's not. It's a linear function, actually, right? Because the only thing that's being exponentiated is the e, and it's to the third power, not the 3x power. So remember, if e is about 3, this is approximately the derivative of 27x, right? So what's the derivative of a linear term? It's just its coefficient, yeah, e cubed. So just because it has something that looks exponential doesn't mean it is. So you'll be baited into problems like this. Now, if you wanted to use the product rule, you could. The derivative of e to the third would be itself times the derivative of the exponent, which is 0. It wipes it out anyway, the first term. So the answer is just e cubed. All right, another application, example 6. Find the coordinates of any points where x e to the x has a horizontal tangent line. We want to know where the function has a horizontal tangent line. So what's our plan of attack? What are we going to do? Take the derivative and set it equal to what? 0. Good. If we can find the derivative, that's the tangent line equation. We want to know it's horizontal. That's where the slope is 0. So let's go ahead and find it. We'll use the product rule. So it's going to be 1 times e to the x plus x times the derivative of e to the x is itself e to the x. And now we set it equal to 0. Once something equals to 0, we attempt to solve it probably originally, first and foremost, by what method? Factoring, right? Factoring. And so the first rule of factoring is to look for a common factor. Well, hey, we have a common factor of e. So when you factor it out, you're left with 1 plus x. And it's always a good thing to quickly mentally redistribute to make sure you get the line above. And we do. So we set them both equal to 0. Either e to the x equals 0 or 1 plus x equals 0. But what values of x is e to the x equal to 0? 1? Well, if you plug in a 1, you get e to the first. That's like 2.7. Very good. There's actually none. If you think about it graphically, e to the x has a horizontal asymptote at 0. It gets smaller and smaller as you go to the left, but never equals 0. If you try to take the natural log of both sides, the natural log of e to the x is x, you get the natural log of 0. What's the natural log of 0? Undefined. Okay? So this piece here, however you want to think about it, has no solutions. It could be that there are no solutions. That's fine. So now this one's linear. 1 plus x equals 0 and x equals negative 1. So that must be my only solution. That function has a horizontal asymptote at x equals negative 1. Now, if it says find the coordinates, the points, that's going to be an ordered pair. So the point is -1, comma. And how do I find the ordered pair, the coordinate that goes with -1? Plug it back into the original. Good. Because remember, the original is your y value function f of x machine. So you're going to get -1 or negative e to the negative x power. Or, sorry, negative e to the negative first power when you plug them in. So that's one way to write it. Or you could write that as -1. You could write that as -1 over e. That's another nice way to put that final answer. Multiple choice version. Okay, any questions so far? We just finished page 2 of 4. That means we're about halfway done. All right, we have 5 minutes left. Let's see if we can finish example 7. Find the equation of the tangent line to this guy at the point 1e. Equation of the tangent line. What do we need for the equation of a tangent line? We need 2 things. Point and the slope. Well, look at here. We actually have the entire point. Usually we're just given an x value and a function. We have the entire point. All we need is the slope at that point. So we're like halfway done with this problem already. We just need to find the slope at the point. That's going to be the derivative. Now, you could go ahead and take the derivative of each 3 terms separately, right? The first term is going to require a product rule. The second term is going to require a product rule as well. So there's already 4 terms plus the derivative of the last one. That'd be 5 terms total. When should we simplify? Late and never? Early and often. Could we factor the e to the x out first? And if so, would that make it easier to differentiate? Well, let's at least try it. If I factor out the e to the x, I get x squared minus 2x plus 2. That should make it easier to differentiate because now it's just one product rule. So look for that kind of thing before you start. So now y prime or dy dx is the derivative of e to the x is itself, e to the x, times the second just goes along for the ride. Now what's kind of funny is if we stop right there before we do the second term, if an administrator walked in and looked at the top line and the bottom line, they would think that we actually hadn't done anything yet on the right-hand side, right? Because it looks exactly the same. They wouldn't really know that we've already differentiated the first factor because they don't know calculus, right? And then plus, now the first term goes along for the ride, or the first factor, I should say, times the derivative of the second factor, which is a polynomial, 2x minus 2. Okay, so now I want to find the slope at the point 1e. Is it worth factoring out the e to the x again? I don't know if it is. I'm going to try it, just for fun. If I factor out that e to the x, I'm left with x squared minus 2x plus 2. If I factor out that e to the x, I'm left with a plus 1, which I distribute and just expand it out and get 2x minus 2. So because this is a plus 1 right there, when I factor it out, I can distribute the plus 1, so I'm just left with that. This gives us a nice, tidy, cleaned up version of y prime. If I combine like terms, I get x squared. Look at this. Those cancel. And 2 minus 2, those also cancel. So we're left with y prime equals x squared e to the x. That is a really nice, good-looking version of the derivative, huh? So what do I need? What did I do that for, except for fun? Good. I need to find the slope at the point. So y prime of what? What are we plugging in for x? 1. Good. We get 1 squared is 1 times e to the first. That's e. So the slope is e, and the y value is what? E, right? So the equation of the tangent line is in Taylor form, y equals the y value of e plus the slope e times x minus the x value of 1. Now, on a free response, that'd be a great place to stop. But if this were a multiple choice question, I would probably not have that as an answer choice. As we get closer to the bell, let's just distribute and see what happens. I get e times x minus e. And what happens with your e's? They cancel, giving you your final answer, which is x. Now, that's not e to the x, that's e times x. That's the line that passes through the origin with the slope of e. Up e over 1, up e over 1. All right, did you have a good time today? Yes, we did. Okay. Hopefully, fingers crossed, I'll be here tomorrow, and you'll have your little quiz over inverse trig functions, okay? Have a good day.